So this section of the note is on random vectors. So let's suppose x is a random variable and it lives in Rp, so there's p different random variables. Then we can say that the expected value of x, or sometimes called the population mean vector of x, so we're going to call this mu, where mu is the expected value of x. Similarly, we can define the covariance matrix of a random vector x, and we're going to call that most often sigma. So we write sigma is the variance of the vector x, and this is a vector also in Rp. So this is a matrix in Rp cross B. Okay, this is a p by p matrix, and it's equal to the expected value of x minus expected value of x times by x minus expected value of x, all transposed. As I say, this is a p by p matrix. Now suppose that we've got two random vectors, x and y. Let's suppose we want to know the covariance between them. Well, the covariance between x and y is just defined to be the expected value of x minus the expected value of x times by y minus the expected value of y, all transposed. And if x is p-dimensional, y is q-dimensional, the covariance will be a p by q dimensional matrix. So recall that expectation is a linear operator. So if A is a constant matrix, and I suppose it's an m by p constant matrix, then the expected value of A times x is just A times the expected value of x. Similarly, if B is a constant vector, and I suppose it's in Rp, then the expected value of x plus B is just the expected value of x plus B. So this leads to properties of the variance operator. So the variance of ax plus b, when x is a random variable and a and b are constant, is just a times the variance of x times a transposed. Hopefully we've seen this before. We can also consider what happens to the covariance between two variables. So let's consider the covariance between ax and by, where x and y are random vectors and a and b are constant matrices. Well, this is just a times the covariance of x and y times b transposed. So now let's consider estimators. So mu, which is the expected value of x, and sigma, which is the variance matrix of x, these are properties of the distribution of x, or parameters if you like. Okay? And typically there might be unknowns, so we might say they're unknown population quantities. So we might want to try and use data to estimate mu and sigma. So the sample mean that we saw in the previous video, so that was x bar, which is just 1 over n times the sum of the xi's. Okay. The sample mean is often used as an estimator of mu, and in particular it's an unbiased estimator of mu, which means that its expected value is mu. Similarly, the sample covariance matrix of the samples x, which we called S, we defined this before to be 1 over n, the sum of xi minus x bar times xi minus x bar transposed. So this is our sample covariance matrix. This is a biased estimator of sigma. So it's often used as an estimator of sigma, but in this case there is a bias in that estimator, and we'll talk more about that later. So this is a biased estimator of